index construction, as I told you, this is regarding the contents, the index which we met already in chapter number 3, that is inverted file or posting file. So that one here we are going to construct using 1 second. Okay, so index construction, as I told you, we will be designing some index algorithms. This index algorithm, in order to design this, we need to understand hardware constraints. Okay, so what are the hardware constraints here? We need to know all those normal, typical hardware basics for a computer. So when building an information storage retrieval system, so we need to know the transfer time, transfer clock cycles, and also we need to know how to access the data. So these are some hardware basics. Yes, you can see here access to data in memory is much faster than access to data on disk. So in order to access the data, we will be using memory instead of using the disk. Since the access in memory is faster than access in disk. And also we have some clock cycle constants, some catching constants you can see here. So these are some system typical parameters. Okay, so the seek time is the time needed to position the disk head in a new position. Transfer time per byte is the rate of the transfer from disk to memory when the head is in the right position. So these are some system parameters which we will be using in our calculation. So average seek time is 5 milliseconds. Then transfer time per byte 0.02 microseconds. Processor's clock rate 10 to the power 9 per second inverse. Then low level operation for this 0.01 microsecond, and size of memory, it can take up to several gigabytes, and size of disk space, it can be 1 terabyte or more. So this, keeping these system parameters in our mind, we will be calculating some sorting time, some transfer time and all. Okay. So for example, you can see here in this example, uh, we are referring the system parameters given in the previous slide. So in order to transfer 10 megabytes from disk to memory, we need 0.2 seconds. around 0.2 seconds. How? So that calculation is given here. So 0.2 seconds. So if it is stored in as one chunk, but up to 0.2 plus 100 into 5 into 10 to the power 3, which is equal to 0.7 seconds if it is stored in 100 chunks. So we need to move the disk head up to 100 times. That's why we have multiplied by 100 here. So these calculations are explained here. 10 megabytes, which is equal to 10 to the power 7 bytes. And so as you can see here, then which will be multiplied by the seek time. So seek time is, transfer time per byte is 2 into 10 to the power 8. So 2 into 10 to the power 8 per byte into 10 to the power 7 is nothing but this, which for 10 megabytes, if we convert into bytes, it is 10 to the power 7. So by multiplying these two values, we got 0.2 seconds. So average seek time, if you calculate for average seek time the given here in the system parameter table is 0.5 milliseconds, which is 5 into 10 to the power 3 seconds. So 5 into 10 to the power 3 seconds into 100 for 100 non-contiguous chunks. So 0.5 seconds and average transfer time. So you have to add this transfer time per byte plus your average seek time. So we got 0.7 seconds for transferring the data from disk to memory if it is stored in 100 non-contiguous chunks. So, and sort base index construction. This is normally our inverted indexing, which we have done yesterday. Okay, inverted file or inverted indexing. So, index construction algorithm for larger collections using disk instead of memory. Using disk instead of memory. So, will it be possible, or if there is any disadvantages if we use disk instead of memory, that we are going to discuss. As it is said that accessing data from the memory is faster than accessing data from the disk. So we need to scan the documents for each term. So this is for inverted file, the steps, okay. The last class, yesterday's class, which we had done our revision on inverted file, that is here. So scanning the documents, then we need to find out the term and the document frequency, and finally the sorted posting list will be created. So in order to sort like 10 to the power 1, 2, 3, 4, 5, 6, 7, 8, 10 to the power 8 records, then it will be very slow because as it is said, accessing data using the disk is slow. So if we have more number of records, suppose if we have
Excuse
less
me, ma'am.
number of,
Someone is trying to enter the class, ma'am.
okay, okay. So suppose if we have a lesser number of terms, lesser number of records, so using disk may be acceptable. But when your number of records is more than huge collection, it has large number of values, large number of terms. Suppose for this particular example, 10 to the power 8 records, 10 to the power 8 terms, then checking your document frequency, checking your document frequency and looking up all these things and transferring it from the disk will be very slow. That's why instead of that one, we will be using block sort based indexing. So how is it slow? So you can just check it here. You can find out the time for sorting. Time for sorting can be calculated. Suppose if you have 10 to the power 8 records on disk, then for every comparison, it may take around 2 disk seats, 6, and time could be sorted with this number of comparisons, n log 2 n number of comparisons. Then how long would this take? So we are referring the system parameters, and using the system parameters, we will be finding time for sorting. So as it is said, every comparison took 2 disk 6, it is 2 disk 6 time into n log 2 n seconds, because we have this number of comparisons. So multiplying these two, we will get time for sorting. You substitute the values and we got around 307 days approximately in order to perform the sorting for 10 to the power 8 number of terms. So that's why, again, this is the same explanation which we have done in the earlier slides. How does average transfer time? It takes around 0.2 seconds, and average transfer time for 100 chunks, it takes around 0.7 seconds. This is for one chunk and this is for 100 chunks. So here it comes. So block sort based indexing. So in order to make index construction more efficient, we will be using our term IDs and document IDs. Okay, so block sort based indexing, we have certain steps here. The first step is segment the collection into parts of equal size. So your blocks will have equal size, and then you have to sort the term ID and document ID pairs, and after that we have to store the results on the disk, and finally we will be merging all intermediate results into a final index. So coming to the next slide, so this is the algorithm, so you can see the example here. So this is one block, this is one block. So it should be of equal size. That means it contains 4 items or 4 terms. Here also it contains 4 terms. So it means these two blocks B1 and B2, suppose if we consider as B1 and this as B2, the second one, then these two are of equal size now. So we will be taking if Brutus is present in D1 and D. So for this particular first block, Brutus is present in D1 and D3. Caesar is present in D1, D2, and D4. This means D1 is nothing but your document IDs. Novel is present in D5, Wit is present in D1, D2, D3, and D5 respectively. And also you can check the second block. For the second block also, the document IDs are given. Now this B1 and B2, block 1 and block 2 being merged here into the block merge. So the third block is called as block merge or B merge. So block merge here, the document ID is sorted and also the terms will be sorted. So Brutus, Caesar, Julius, killed, noble, wit. So these are sorted terms, and also the document IDs will be sorted. So D1, D3, D6, D7. So after merging these two, we finally got our block merge block. Okay, so merging in block sort based indexing. So we have two blocks forcing list to be merged. They are loaded from the disk into memory. So these two blocks are loaded from the disk into the memory, merged into the memory, and finally written back to the disk. Why? Because accessing the data from the memory is faster than accessing the data from the disk. That's why we recording the blocks from the disk, and we perform the merging operation into the memory, and finally the merged block is written back to the disk. So example, so here also what you can do is you just construct two blocks of equal size. Okay, two blocks of equal size. This is like it depends on how you split the blocks. If you have three blocks, then it must be of equal size. If you have four blocks, then it must be of equal size. So since we have lesser number of document here, since our collection is less, so we can just put two blocks. So if you have more number of collections here, suppose D1 up to D10 or D1 up to D20, then accordingly you can separate the block into of equal size. For example, 5 blocks if you have 20 number of documents, 20 number of collections. So you can split up to 5 blocks of equal size. So if you have 5 blocks, then there will be 4. It depends on the number of terms. So here for this particular example, I think this one we have done in our last class also. So it should be sorted one. The dictionary should be sorted. That means the term should be sorted, and your document IDs should be sorted in each block too. So here for this particular example, we have two blocks, and here I have written only one term, so you can write all the terms here. Okay, you can write all the terms. If you have 5 terms here, you should also have 5 terms in block 2. So based on the data given here in the documents, you separate the terms equally and identify your document term pair. And this B merge is merging of these two blocks. So first, these two blocks are loaded from the disk, and they are merged in the memory, and then finally written back into the disk. So why we load the blocks from the disk is that uh, we need lesser time for accessing the data from the memory than accessing the data from the disk. So this is block sort based indexing. And now we have distributed indexing. So in distributed indexing, we will follow one map and reduce schema. We will follow one schema. One second. Let me share that one. Block. One second, one second. Distributed indexing. Okay, so distributed indexing. So here we will follow the schema called map and reduce schema. So which is here map and reduce schema, distributed indexing. So map and reduce schema, this is nothing but some general architecture of a distributed computing. So we are going to use an architecture based on distributed computing. So here also we will be having term ID and document ID pair. So this pair is known as key value pair. Key value pair, key will be your term ID, value will be your document ID. So distributed indexing we can use in large computing problem, and this indexing will be in the form of key value pairs. So key value pair is nothing but the term ID and document ID. So we will see the example directly here. So the schema of map and reduce function. Our mapping function is nothing but we will be taking the input. Input is our web collection. Okay, input is our web collection. And reduce schema, it will take into the pair of key and list of v. Key and list of v, which is our output. So this will be our output. Our input will be list of key value pairs, term ID, document ID pairs, and our mapping function, which is key and list of values. That means list of document IDs. So this will be our output. So you can see here for mapping function, we can take it from a some web collection, and list of term ID and document ID you will be writing in the mapping function, and in the reduce function you will be writing key, term ID, list of V, that means list of document IDs. So that will be written here, and finally this will result our output. Our output will be our posting list. Now you see the example here. So we have written C. C is nothing but your term ID for Caesar. Okay, term ID for Caesar. And this C apostrophe ED conquered. This is also term ID for conquered. So sometimes when the term is having short length, we can directly use this particular term. Okay, otherwise if the term has a longer number of characters, then you can just use the ID representing it. Okay, but normally we will be referring as term ID and document ID. So for mapping function in document 1, we have two sentences here. Caesar came, Caesar conquered. And in document 2, we have Caesar died. Okay. So now this mapping function, you can see here, list of K and V, term ID and document ID. So you can see CD2. So this is your term ID, this is your document ID. Type is another term ID. D2 is document ID. C, D1. So we have written it in the form of term ID and document ID. Now coming to the reduce function. For reduce function also we will be in the form of term ID and list of document IDs. So term ID and list of document IDs we have written down here. C is our term ID and list of document IDs D2, D1, D1, because C is present in D2, C is present in D1 and D1 two times. So document ID for that is D2, document ID for Kim. So we are writing the term ID along with the list of document IDs. And final output is posting list. So posting list is where you write the term and you write the document ID along with the frequency. So for D2, C is there in D2 two times and is there in D1 two times and in D2 one time. Died is there in D2 one time. Came is there in D1 one time. And conquered is there in D1 one time. Okay. So this is the output for reduce function. So in distributed indexing, we will be using map and reduce function. Now, next one, next is index compression. So index compression, recently we have been discussing about this, so I don't need much explanation on this. But anyway, we will just go through once. Index compression, we will be employing certain compression techniques in order to achieve efficient IR system. So here we have Heap's law for estimating the vocabulary size, and we have Zipf's law for modeling the distribution of the terms. So Heap's law, we use this function in order to calculate the vocabulary size. Okay, so term if t value is greater than 10 to the power 5, then we can use this parameter values. So b equal to 0.49 and q equal to 44. Why we use these values when t equal to 10 to the power 5? Because we use this values in order to get your excellent fit. Okay, your fit, the fit is excellent for t greater than 10 to the power 5 for parameter values b equal to 0.49 and k equal to 44. So it is best suited in this parameter values when t greater than 10 to the power 5. So example is here, and Zipf's law. Zipf's law, it is like your rank frequency and rank distribution is an inverse relation. Okay, rank and frequency distribution is an inverse relation. So this explanation I have already done here. So when you have rank lesser, your frequency will be greater. So rank lesser, frequency greater. Rank lesser, frequency greater. So this shows that rank frequency has an inverse relation, and the most frequent term can be calculated using this one. Okay. So here it states that if T1 is the most common term in the collection, T2 is the next most common term, and so on, then the collection frequency of the ith most common term is proportional to 1 by I. It's nothing but it's an inverse relation. So now we have another statement for finding the probability and checking the probability value, like rank and probability. If you multiply, so it will get a constant value A. So A is a constant value. So in most cases, A value will be similar to 0.1. So that calculation we have done here. So rank 1, so this is has the highest frequency. Highest frequency, so rank is 1. Then we calculate the probability and we calculate A also. So since we calculate the probability and multiply it by your rank, then we almost get a constant value A. So here 0.06, if you take approximate, it can be written as 0.1. And for the second value 0.05, you take approximate, it's almost similar to 0.1, like this. So our probability, if it is multiplied with the rank, then we will get a constant value A, which is similar with 0.1. And dictionary compression recently we have done. So dictionary compression, we can use fix with entries, and also we can use dictionary as a string. So dictionary as a string has lesser space requirement comparing to dictionary compression, because in dictionary compression using fix with entries, we will be assigning a fixed width which is 20 bytes for every terms in the collection. So every terms may not have the same length. Some terms may have only 2 characters, some terms may have only 4 characters, but they have assigned fixed width as 20 bytes, which means up to 20 characters. So simply we are wasting lot of bytes using fixed width entries. So for space requirement for Reuters is a database we refer for this example calculation, and space requirement using fixed with entries is 11.2 MB. Whereas in dictionary as a string, when you consider the whole as a string, then we won't be uh, considering your fixed with entry. So we will be considering the average length entry, which is 8 bytes. Average English length character, English word character length is 8 in an average. So we will be considering only 8 bytes. And here in your term, this one, 4 bytes for document frequency, 20 bytes for the term, and pointer to posting list 4 bytes. So here we will be using a term pointer. We will be using a term pointer which will be pointing to the beginning of the term, and that needs about 3 bytes. So when you do calculation for this dictionary as a string space requirement, the calculation is shown here. It takes about 7.6 MB. So the space requirement is reduced by one third from 11.2 MB using fixed with entry to 7.6 MB using dictionary as a string compression technique. And we have block storage here also. It is somewhat similar with dictionary as a string, but this will be considered, the algorithm is based on block sort based indexing, where we separate into equal size blocks, and here we will be keeping a term pointer only for the first term of each block, whereas in dictionary as a string we put the pointer for every terms in the collection. But in block storage, we will put the term pointer only for the first term of each block. So obviously, instead of pointing all the terms in the collection, we will be pointing only for first term of each block. So automatically the size will be reduced. But here we add another 4 bytes because of this term length which is specified here. For every term at the beginning of it, we have specified a term length. If system has 7 characters, so 7 bytes. So in this 7 bytes, we will put the term pointer. So if a block contains 4 terms, then this remaining 3 terms will be putting the term pointer. So if we put in 11 term pointer, then from this it starts a new block. So for this also, calculation savings, this has been explained earlier. So with this we got about 7.1 MB. 7.1 MB. Again another 0.5 MB has been reduced. So example also we have done in our last class, and searching steps also we have done. But here they have put one condition. When you increase the block size, we can get better compression. When you increase the block size, we can get better compression. But increasing the block size can lower the speed of searching the term, speed of term lookup. In our word, we say term lookup. So when we increase the block size, we may get better compression. The size may be reduced more, but it may take lower time to find the term, or the speed will be slow for term lookup. That has been explained here. For searching using an uncompressed dictionary, it may take about 1.6 steps using this example. And for k equal to 4, that means your block size becoming 4, then it may take about 2 steps on average. That means this has more time to search the uh, term from the collection. Whereas in term of compression size, so it may be reduced up to 6.8 MB from 7.1 MB. So normal block storage it may be 7.1 MB. So this means we can understand from here, if we increase the block size, the compression size may be, we may have better compression size, but this will take longer time for term lookup. And front coding also we have done. We are just taking out the identical prefix. We are just taking out the identical prefix, and it will be encoded by marking the end of the prefix with asterisk star, that means star, and replacing it with diamond symbol in subsequent terms. So in subsequent terms we will be replacing it by diamond. So here for this particular example, up to automat, AUTOMAT, it is same for all the four terms here. So this is considered as identical prefix that has been written here along with the term length 8. Term length is 8, and we have written automat. So for automata it is 8, but we have taken identical prefix up to automat. So automat is written here. Then this will be encoded by the end of the prefix with asterisk. So star is written here. Then this is the missing word. So A is missing from automata, right? So that A is written here and followed by a diamond symbol in subsequent terms. So in subsequent terms, we have written diamond symbol here. Similarly, for the second term, E is missing. So E is written here and it is followed by a diamond symbol. And for the third term, automatic, IC is missing. So IC is written here followed by subsequent diamond symbol. And for the last term, ION is missing. So ION is written here. So at the end, you don't need to put your diamond symbol. Okay. So this is front coding. So front coding, again it will reduce more because for every terms in the block, so we don't need to write the term length. We are just writing it for the first one, and we don't need to write the term length. And also we don't need to write the whole term again and again. So for automata, up to automat it is written. Again for automat, the second term AUTOMATE, we don't need to write AUTOMATE. We have to just add only E. Similarly for automatic also, we don't need to write the full length automatic. So since up to automat, identical prefix has been taken common, the remaining letter missing, that is IC only, we need to write. So for automation also same, up to automat it is already written as identical prefix. So the remaining ION only we have to write. So obviously this also will reduce your space requirement. So you can see a brief comparison here. For fixed width, we got about 11.2. Dictionary access string, we got 7.6. With block storage, we got 7.1. With block storage plus front coding, we got about 5.9 MB. Now, the last one, posting. Where is it? Posting file compression. So for posting file compression, one second. So we have done this recently about posting file compression also. The first one, the compression which we have done was about dictionary compression. That means the term compression. Now for posting is nothing but your locations. So location also, when you have larger number of documents, you have more number of posting list. So that has to be again compressed. That's why we need both compression for dictionary as well as compression for postings files. So again, taking the database from Reuters for your reference, it has about 8 lakhs documents, 200 tokens per documents. So every documents may have contain about 200 terms in an approximately about 200 terms and 6 characters per token. So 6 characters per token. On an average, it may have about 6 characters per token. So 6 bytes. Okay, it may have 6 characters per token. So 6 bytes and about 10 to the power 8 postings. So you may have 10 to the power 8 postings. So based on the database from Reuters. So now instead, when you have larger number of posting, 10 to the power 8 posting is too much, right? So instead of saving all the 10 to the power 8 postings, what we are going to do is we will be saving the gaps instead of saving the document IDs. Because document IDs, if you have 10 to the power 8, then from 1, 2, 3, 4, 5, 6 until 1 lakh, 2 lakhs, 3 lakhs until if you reach 10 to the power 8 postings. So those are called document IDs, right? For us, posting files are nothing but our locations. Locations are our document IDs. So document IDs, instead of saving up to 10 to the power 8, we are going to save the gaps. So these gaps will be again encoded instead of document IDs. So in our memory, we will be storing the gaps instead of document IDs. For example, you can see here page number 2,883,042 and the second document ID is 2,83,043. Third is 2,83,044. So instead of saving 2,83,043, we will be saving 1 because the previous document ID and the current document ID has one difference. That means the gap is 1. So we will store the gap 1 only. Instead of saving 1, 2, 3, 4, 5, 6 bytes, we will be saving only 1 byte. And similarly, for the remaining words also, we will be storing the gap instead of document ID. But one point here to be noted is the first document ID is left unchanged. So as you can see here, the third term arachnocentric, for arachnocentric, the first document ID is 2,52,000 and the second document ID is 5,100,000. So in gaps, the first document ID, we are saving the first document ID 2,52,000 and we are saving the gap. So 2,52,000 and 5,100,000. The gap between them is 2,48,100. So we are saving these two gaps. So if the terms are less occurring, then you may have almost similar, say for this particular example, since for the and computer, the gaps are very less. It is only 1, it is only 5, it is only 43. But since they are frequently occurring words, suppose for this arachnocentric term, it is less occurring word, so the gap is more. So the gap is almost similar to the document ID. So there will be cases like this also. Okay. So the gap explanation is done here. And for gap encoding, as I told you, for gap encoding, we need to encode a gap instead of document IDs. For gap encoding, we have variable encoding. Variable encoding is again two types: bytewise compression encoding and bitwise compression encoding. So for byte coding, it is here. So byte encoding, variable byte encoding. Here, the gaps are encoded using an integral number of bytes. So the first bit, the continuation bit of each byte indicates whether the code ends with this byte 1 or the code ends with 0. So this byte encoding, this is the first byte, this is the continuation byte. It has two sections. Okay. So based on the gap I values given here, so we need to write the corresponding variable by encoding. Okay. Yeah, that's all I think. So for your exam also, there won't be questions on encoding part, because encoding part is like five is the variable byte encoding for 5 is this one. So this part we don't do. So for this part there won't be questions, and as I told you, for this we need a separate class to study all these mathematical terms and coding and all. So this part there won't be questions, but we can have questions on posting file compressions. Okay, not the encoding part, but what is posting file compression, and how do we do the compression? How do we store the gaps? And instead of saving the document ID, we store the gaps like this. So what is posting file compression, and how do we do it? So that kind of questions may be there, and this gap explanations you may be there, and saving the say for this third term arachnocentric, the first document ID is to be saved, right? So like this, some multiple choice type questions can be there from this part. Okay. And for dictionary compression also, differences, then sizes, space requirements, questions may be there on space requirements, and the differences between the compression techniques. So what is the difference between fixed width entries and what's that, dictionary as a string compression technique? So what is the difference, and like that, what is the space requirement for front coding, what is the space requirement for uh, block storage based on Reuters database, like that questions may be there from this compression. And also questions can be there from heap slow, jeep slow, block sort based storage. Okay, all questions will be multiple choice type questions. And I think for your midterm, it will be about 20 marks and 10 marks from Viva, I think. Okay, so 20 marks. So in that 20 marks, if possible, I'll try to do all subjective. Otherwise, I may put one or two subjective questions. Okay, like how we do in our previous semesters. Same like that. So some few questions will be from subjective, and most of the questions will be coming from your in the form MCQ. So like that, questions will be there. Okay. So I think let's finish the exam tomorrow. I don't need to do class, because if I have to do class tomorrow, we have to take the new topic. This chapter, which is uh, scientific indexes. Okay, there will be the analytic indexes, and there will be Jones coding, there will be here. So this is we will do on next class. Okay, today let us wind up. How those first I will inform you. Up to this is the midterm syllabus. Okay, one is done now. And today we have the revision. So once again, your syllabus is Boolean retrieval along with the introduction part, and next one inverted index or inverted file, and next one is index construction, and finally along with index compression. Okay, so these four chapters will be there for your midterm. Okay, so before we wind up, let us take your roll call.
Present, ma'am.
One second, one second. So roll number one,
Present, ma'am.